Tuesday, no less. And we're doing this because we have to speak to Dominic, because Dominic is doing some insanely cool things. Dominic, would you mind sort of letting people know who you are and what it is that you do, if there's time, because the list of stuff you're up to is extraordinary.
Yes, of course. So I'm Dominic Dirkx. I work at TUDelft in the Netherlands in Faculty of Aerospace Engineering. And my field is astrodynamics, which is the study of how things move through space. And I'm involved in various projects. One that I work a lot about and I'm very passionate about is the JUICE mission.
Yeah.
The Jupiter Icy Moons Explorer that's now on its way to Jupiter.
Right.
We have to wait a little while. It won't get there until 2031.
Right.
In a few months, it will first fly by Venus on this little tour through the solar system. And by the time it gets to Jupiter, it'll make lots of flybys of the moons of Jupiter. And from doing all sorts of measurements there, we'll very accurately measure how does a spacecraft move, which tells us something about the gravity field of the moons, what they're made of on the inside. But also one thing I'm very interested in is how the orbits of those moons around Jupiter, how they very slowly evolve in time, because that tells us something about how the whole system has evolved. Because we know more or less what these moons are like now. We know 3 of these very big moons have water oceans under their surfaces.
That I get so exciting about that.
Yeah,
that stuff is just fantastic. Yeah.
This is something that a few decades ago, was thought to be quite rare. And before that, maybe even impossible. But now we know lots of these icy moons in the solar system have deep subsurface water oceans. We don't know exactly what the composition is, but we know it's liquid water like we have here on Earth.
Yeah.
And if we look at Europa, that's a fairly, small-ish moon compared to some of the other ones. But underneath its ice crust, it has more liquid water than all of Earth's oceans combined.
Wow.
Yeah, which is insane when you think about it. It's so deep in the solar system. It's 5 times farther away from the sun than we are. The surface is really super cold, frozen solid. Under the surface where there's still heat, these oceans are kept liquid. And one of the things we're going to do with the JUICE mission is see how have these oceans evolved, because we know they're liquid now, we know they're there now. But what have their conditions been over the last few million and billion years? Have they been stable enough for life maybe to form there? These are some of the questions, we won't entirely answer, but make a contribution to.
How on earth do you figure that out? Like how do you go back? How do you look back that far? What sort of stuff are you using to do that?
So conceptually, it's very simple. Like many things, you get into the details, it becomes a lot of fun. But
I'm with you on that. Yeah.
But so what we'll do with the JUICE mission and also NASA's Europa Clipper mission is we'll measure very, very accurately how fast are the orbits of the moons moving away from Jupiter. They're very, very slowly moving away from Jupiter due to the tides, both on Jupiter itself and on the moons. And then
because of the water on the planets, that's what's causing them to change orbit?
No, so it's the this is an interesting thing. So when I say tides, to you that means ocean, right? Like water on the Earth that goes up and down on the beach.
Yeah,
that's one of the things that tides do. But tides squeeze the whole Earth, just like they do the ocean. So the whole Earth, the ground under your feet, goes up and down by 0.5 meter, more or less, every day.
Wow.
The ocean a little bit more because it's easier to move.
Right.
But this change in shape on Earth, it's about 0.5 meter. On some of the moons of Jupiter, it's much, much more because they're closer to Jupiter. Jupiter is much bigger. Wow. And because of these tides, the orbits slowly move away from Jupiter. It's just like our moon.
Yeah.
The tides on the Earth and the moon cause the moon to slowly move away from the Earth.
Wow. Give me an idea of how much? How far are they moving?
For our moon, it's a few centimeters per year.
Oh, that's still a fair distance.
Yeah. Wow. So it's and on Earth, it's now fairly easily measurable. We have laser retroreflectors. We shoot lasers.
Yeah.
To the moon. We receive them back.
Yeah.
And what we then do with this is basically we take the equations we have for how the moons move. We take our measurements, we add a minus sign, and then we go backwards in time.
Oh, wow, of course, so you just do it. Wow, yeah,
Yeah,
okay. So you can see how close they were, you can see and you'll see the effects of how liquid the ocean is and how solid it is compared by just by studying those numbers.
yeah, yeah. And
Wow.
it's the farther you go back in time, the more uncertain this becomes, because if
Mm,
the orbit changes, the heating due to the tides changes,
mm.
which causes the interior to change, which again causes the tides to change. So it becomes the details of this are things that I don't know too much about, but I have a bunch of colleagues here who know loads about that. My job is going from the measurements that come from the spacecraft
Yeah,
to saying this is how the moons are moving now,
right.
and I give that to other people, and they'll say what that means, and then we go back and forth. They ask me, well, what if you change this in your model? What happens?
Wow. And how many people are in your team?
So the people who work for me directly are about 5 or 6.
Right.
The people in our whole department in Delft, so all of space engineering, that's quite broad.
Hmm.
That's including PhD candidates, I think close to 100 now. But
Wow.
those that cover a lot of different topics. And the whole JUICE mission, everything is, I think, 2,000
Right,
people
right.
working on it.
Well, and that's got people from all over. We got from all over the place, right? It's
Oh,
not
yeah.
just yeah. So okay, so how do you get into this? How did you were you literally just like looking up at the moon as a kid and going like I want to know how that works or what?
So, as far as I can remember, as early, as young as I was, I always thought space was cool.
Yeah.
I don't know why,
How can you
but
not? I mean, really? How can you not? I mean, like it's yeah.
yeah. So I remember going to the library and getting all these cool books with cool cutaway pictures of what
Yeah.
planets look like. So I
Yeah.
think it's really cool that now I'm making those figures. It's still
Yeah.
surreal to me. One thing I think is also really cool. There was a nice full circle for me. I remember when
Mhm.
I was 12.
Yeah.
The Cassini spacecraft launched to Saturn and its moons.
Oh
I
yeah.
was a 12-year-old kid watching it on TV,
Yeah.
being fascinated, and scientists were on TV explaining what this mission would do and how and why. And I remember my mother was sitting next to me, and I thought all this stuff was cool, and said, maybe when you grow up, you'll be doing that sort of stuff. And then 25 years later, JUICE launched after one day delay, but launched at Jupiter. And then I was in the lecture room here with camera crews on the national news, and I was
You
explaining to
you were the guy. Oh, that's
12-year-old
fantastic.
what the mission would do.
Wow.
So that was really cool.
God, that's great. And were your parents into this stuff as well? Were they in the sciences as well?
Not
Or
not so. My mother, not really. My
Mm.
father, a little bit. I also got a very old science astronomy book from him from the 60s or 70s. It was
Yeah,
all outdated, but I still read it 10 times front and back.
right, right.
But they were very much stimulating.
Yeah, yeah. I found the same thing with my mother was always studying something. She went back to university quite
Yeah,
late in life after having 4 kids, but it's that same thing of just like I want to know what
yeah,
explain. Let's like what else? What is there
yeah.
to learn? And so what was the path you took? How did you?
So
You want to do this. What were the? Where did you grow up, by the way? Where was where?
uh, in the Netherlands,
Okay, yeah,
in a town called Leiden, very close to here,
yeah.
where, funnily enough, the big solar panels for JUICE were built there by
Oh, great.
Airbus,
Oh,
uh,
fantastic. Okay.
just a few kilometers from where I grew up.
Did you go and see them?
No, sadly not. But maybe I could have, but I didn't.
I'm all about the impromptu visits. I love the sort of, oh, hi, do you mind if I have a look?
But
Uh,
I am every now and then at ESTEC, that's
mm,
ESA's biggest research center, which
yeah.
is close by in the Netherlands, almost cycling distance from here. And when I'm there, sometimes someone can give me a tour of what's in the testing facilities. And
Hmm.
sometimes they have the spacecraft there that's going to be sent to wherever. They're then put on the big shakers or in the solar system
Yeah.
simulator.
I
So it's
can't
really
wait to see
cool
it. I'm hoping to get up there for ESA Day this year.
cool. Yeah.
Have you done that? Have you been to that before?
Yeah.
Yeah.
And I'm at ESTEC a couple times a year
Oh, wow. Okay.
for meetings. Also, one of my former PhD candidates now works there, so I have an easy way to visit
Nice.
if I want.
You're expanding your network,
Exactly.
your nerd network. That's
Yeah,
it. Yeah.
definitely.
Um, so
No,
so so always been in the Netherlands. It was all and is there? I mean, there must be a fair amount of education to get you there. I mean,
yes.
this yeah.
So actually, for a while, I thought sure, space is cool and fun, but I'm not sure if it's something that I want to do for a living. Not sure if
Right.
there's jobs in there.
Well, because
So
there's not a lot of information about how to. I mean, is there? Like
so
you think of astronaut, but that's basically the only thing as a kid you get told is a job that
yeah.
relates to it, right? Yeah,
So, but there's actually there's loads of industry, especially here around
yeah,
Estec, but throughout Europe and US.
yeah.
So if there are people watching and think, oh, I'm not sure if there's jobs in space engineering or space science,
Hmm.
there's well, at least right now, loads of jobs.
Yeah. Is there? Oh, there
But
really is. Like, so there's like they're hiring a lot of people right now.
yeah, so especially I'd say in industry, the situation is still pretty good. There's still
Yeah.
plenty of vacancies.
And it
Uh,
is amazing how many different like parts there are to this. I
oh yeah,
mean, that
yeah.
you can almost find a niche in any department for this stuff.
Absolutely.
Yeah.
And the more you learn about a certain topic or application or mission, the more you
Mm.
realize how much detail goes on behind the scenes just
Oh
to
yeah.
make sure things work.
Yeah,
That
yeah.
you never really, think about.
Yeah,
Um,
it's extraordinary. I think that's part of the fun for me. One of the things I love about film and TV is the technology. I love all the cameras and all the equipment and just how all the tricks they have to do stuff. And I think that I mean it's got to be. I mean the toys you've got to play with got to
oh
be
yeah.
just amazing.
So there's one cool example, many cool examples, but one that comes to mind of something that then happens behind the scenes that you don't really think about is a mission called Gaia,
Yeah,
which is a European mission that just ended its operational life. It was flying for 10 years, and it sounds like the most boring mission ever, but it does so many cool things.
right.
It was just a telescope in space, spinning
Mm.
around its axis, taking pictures of stars. So
Wow.
it built a big catalog of billions of stars.
Right.
So it's trying to see, well, what are their properties, how do they move, what are their colors,
Hmm.
and for my field, for seeing how things in the solar system move.
Mm.
One of the cool things it does is every now and then an asteroid flies through
Oh
its
wow.
field of view, and then
Yeah.
we see exactly where the asteroid is or where the moon is,
Yeah.
and then we can use that to improve their orbit. But something I think even cooler is that part of these models of the motion of the moons of Jupiter, some of the data we use
Mm.
goes back to the 19th century. The
Yeah, there's
19th
like a
century.
historical aspect.
Yeah,
to
so
it. Yeah.
the whole data set that's still being used is almost 2 centuries, 1.5 century old.
Right.
And then there are plates, photographic plates,
Mm.
or written observation that say at this moment in time, written in longhand in a notebook somewhere,
Wow.
this moon was this far away from this star. We know where that star is, and then we know where that moon is.
Mm.
And then from the Gaia mission, we can better model where that star was
Wow.
in 18 whatever, and from that better know, okay, where was the moon in 18 whatever,
Yeah.
and from that better understand how has that orbit of the moon evolved in the last
Mm.
century and a half. So it's
It's
a series of small changes. This improves that, improves that, improves that.
yeah. And that even though the stuff that we can get now is so much more precise, it doesn't make the other stuff obsolete. It's still something that can be used.
Exactly. Yeah, we did a study on that a year back. Sam, the same PhD candidate, who's now at Estec.
Right.
And so he analyzed how useful will this data still be.
Mm.
Because we'll have in the 2030s loads of insanely accurate data from the JUICE mission, from the Europa
Right.
Clipper mission,
Yeah.
that will tell us the range between a telescope on Earth and a spacecraft to about this much,
Right.
which
Yeah.
is crazy if you think about it. At almost a
Oh my
billion
God. No, I
kilometers away.
can't. It's yeah. Yeah. Wow.
And the data from the early 20th century, late 19th century, if it's accurate to 1,000 kilometers,
Mm.
we're pretty happy.
Mm.
So maybe 1,000,000 times worse than what we'll get from the JUICE mission and Europa Clipper. But because it's so much older, it allows us to see how over a long time span the evolution of the orbits of Jupiter
Mm.
has gone. And by combining the two, then we really get the best of both worlds. We saw that if we take just the JUICE and Clipper data, over a small period, we have a very good solution for the orbits.
Mm.
If we try to move that backwards in time, like we want to do to understand revolution,
Mm.
then we see very quickly it becomes unstable. Well, if we add these very inaccurate but very old observations, the whole solution becomes a lot better,
Interesting.
which was really cool. We hadn't expected that much.
And did you go in, and I guess you can't really just sort of scan this stuff, can you? Because if it's handwritten, I suppose you've got to, like, is it just got to manually put that stuff into the models that you're
So
using?
in some cases, yes, but they have now some big machines, one in Brussels, one in Paris,
Mm,
where they can take these very old photographic plates and
mm,
digitize them. They put them into the machines, they scan them very accurately,
mm.
and then that gives us exactly the data that we
Right,
need to do the analysis
right.
for these orbits.
It's funny. This is something that it's sort of a reoccurring thing that I'm hearing from a number of different scientists in a number of different fields, is how they're they're making new discoveries by re-examining
Yeah.
older data. And I know a lot of them are using AI at all in any of this, or
No, not me, but indirectly, yes, people are using AI. For instance, if you have a picture of a moon, you
Mhm.
want to get from this picture of the moon some idea where is it.
Right,
It's quite a complicated process because only a part of the moon is lit. So you just see
right,
sort of a crescent shape,
right.
and then where is the center of that moon, which has craters and it's a funny shape. There are
Mm,
no people using AI models to make that prediction, make their
right.
prediction better.
Right. God, that's amazing. I mean, the tools that are coming out of this stuff is just amazing. I love the fact that it's all just observation. Like, it's all just, you just get as much information down as you can, and even if you don't know how to use it, it's just good to have so that you can, you
Yeah,
know,
yeah,
it's
and what's also really important, so to have lots of observations,
mm,
but something that I think sometimes people don't pay enough attention to is how accurate are those observations.
right, right.
Because if you have centuries of observations, to
Mm,
combine those, you also need to know, okay, the data now is this accurate, data 100 years ago
mm,
was less accurate, but the way your solution for the orbits behaves and
mm,
the scientific results you interpret, how the moons have evolved,
mm.
might become different if you incorrectly say, well, the old data was just as good as the data now.
Right, right,
Instead, you say, if you know the data was a lot worse,
right.
uh,
That has to get taken into
yeah,
account.
yeah,
Yeah. Well, garbage in, garbage out, right?
exactly,
Yeah,
exactly,
yeah.
yeah,
But you're not just studying this stuff. You're actually creating tools that are simulating these orbits, right?
yeah,
Is
yeah.
that
So we're building TUDelft. That's a software library that we've been building for more than 10 years now. As that started already when I did my master thesis, which is a while ago by now.
well put?
Uh,
You should work in the film industry. You're good at
uh,
hiding your age. There you go. Yeah,
yeah.
yeah.
Um, and so we've set that up very broadly to tackle many of the different applications we do in our department, which is this kind of stuff, but
Mm,
also simulating interplanetary transfer orbits, reentry vehicle dynamics, mission optimization. And we
right.
saw everyone lots of people doing research on this, master students, PhDs, some staff members, were
Mm,
all building their own tools from scratch.
mm,
And a few very entrepreneurial PhD candidates at the time thought, no, we need to do things differently. We need to set up our own framework.
right.
Sometime later, made it all open source. And in the
Yeah.
last couple of years, especially, we put in a lot of time and effort to develop the things to estimate orbits throughout the
Mm,
solar system. And we're getting really close to the same level of accuracy that other big or closed source software packages are getting. And
right.
this is something that I think is really, really important because we're already seeing a few cases where two groups of analysts are getting different results. For
Mm,
instance, there's a discrepancy now for the interior of Titan, the largest moon of Saturn.
right.
Cassini, a spacecraft, flew by there a whole bunch of time, collected lots of extremely accurate radio tracking data. So
Mm,
seeing how Cassini changes its motion while flying by Titan,
right.
going through a lot of analysis like the kind I do, we can deduce aspects on its interior.
Mm.
Now there's two solutions. One say the interior is A, the other says the interior is B.
What are the A and B? What
Yeah,
do you what
so
are they?
the A and B is something called a love number. And the love number is a quantity that defines how much the moon gets squeezed by tides.
Right. Okay.
Depending on the interior structure, you can imagine if it's very soft,
Mm,
then it can get squeezed a lot by tides. If it's very rigid, it doesn't get squeezed so much.
right.
And
Right.
there's two solutions. One say this love number is quite low, the other say it's quite high. And this has a lot of implications for what the ocean under Titan's icy crust looks like.
Right, of course.
And also on its composition, how much ammonia is in this water, if it's in contact with rock. And if water is in contact with rock, it's a lot more interesting than if water is in contact with ice on the bottom. As if water is in contact with rock, you basically have the same sort of situation as on the bottom of our oceans.
Right.
We can have these black, what do you call them? Black steamers that spew material and heat from the interior.
The vents that
the
come.
ocean. Yeah, exactly.
Yeah,
and we see on Earth ecosystems that survive just from the heat of those.
Oh, yeah. The extremophiles.
Exactly.
Yeah.
And so we have now these two solutions for the interior of Titan. And we don't really know which one is correct yet. Among others, because
will you get that from Juice? Do you think you'll be able to solve that because of with Juice's analysis?
Juice is going to go to Jupiter.
Oh, sorry, right.
Titan is around Saturn.
Right, right.
But the same.
Too many damn planets.
Yeah, I know. But too many cool work for us to do.
Right.
But so there's also for Juice, these kind of analyses we'll also do. But because
can you translate that? Like if you're studying one planetary system or moons, that I'm assuming that some of that can translate to other ones as well.
Definitely.
Right?
So lots of the mathematical models, software tools work more or less equally well for one or the other.
Right.
For Jupiter, there's a complication that these moons are in a mean motion resonance, that one orbit of Ganymede around Jupiter is exactly 2 of Europa, is exactly 4 of Io.
Wow.
It gives all sorts of funny results in their motion.
Right. You're getting into some funky math there, I imagine.
Yeah.
And they're all interacting with each other as well.
Yeah.
So this,
wow. Yeah.
So is it, I mean, having one singular moon for us, is that, I mean, I guess that doesn't really help much, does it? Because ours is just a completely barren, our moon is not as exciting as any of the watercolored ones, are there?
Well, so if you ask me, I entirely agree. Yeah. If you invite someone who's an expert on our moon, I'm sure they can give you loads of reasons why our moon is much more interesting. Than, not
to say it's not interesting. I guess I was just thinking if there's anything you get from ours. I guess it's not because it's not. I'm assuming there's still some squishing, but not the same kind.
Oh yeah, so our moon, there's still some deformation. In fact, one of my colleagues just helped write a paper to better analyze that.
Oh, okay.
That you can see how one side of the moon is different from another, and how it gets squeezed. But the effect is much weaker.
Right.
Because our moon is mostly rigid. There is probably some liquid in the deep interior, the inner core or outer core. But our moon is much less dynamic than some of these icy moons. If you look at Europa especially, you see all these sort of break lines on the surface that are ice plates that are moving past each other.
Wow.
So there's a lot more going on there.
Right. And also, I guess it's new for us. I mean, we've been looking at the moon for years, so we get blasé about this stuff. And so, when you got into this, did you go straight to Saturn and Jupiter and stuff, or were you? I mean, what was your focus from the beginning? How did you end up with this?
So I sort of went around. So when I finished high school, I thought, I don't think I want to go into a career as a space engineer or space scientist.
You want to be a rock star?
No, the singer, no. Listening, yes, but
singing, me too. No one wants to hear me sing. Trust me.
No. It's if I have a few, I'll try, but not to anyone's. Not to anyone's pleasure except my own.
Right.
But so I decided to study physics for a year, which was interesting, but I noticed it wasn't really for me. And then after that year, I decided, no, screw it. I'll go switch over to aerospace engineering here in Delft.
Wow.
And then from the beginning, I thought, yes, okay, this is it. From when I started.
What was your reticence? Why not right away? What was it that held you back from going to that?
I wasn't entirely sure. First, I wasn't entirely sure if there would be a job for me or suitable for me. Because also, I like building things. I'm not very good at building things. That's also why I now build software, because I'm just not good with my hands, but I like. Yeah. Setting something up that grows.
And just programming is, God, it's such a great, I love it.
Yeah. But so one of the doubts I had was studying aerospace engineering.
Right.
that I had the preconception of it. And engineers have to build things with their hands.
Right.
And if I'm not good at building things with my hands, then I can't be an engineer.
Right.
And sure, there were some courses like that. Those are the courses I was not very good at.
Mm-hmm.
But it's so much broader than I thought it was. And also much more applied. I remember studying physics, thinking, okay, this is all very interesting. But what do I do with this?
What do I do with it? Yeah.
I was 18. I was very impatient. I wanted to do something. And then I came here to Delft, and immediately it was, okay, we learned this, and then we can do that.
Right.
I thought, okay, yeah, now this is where I want to be.
I think that's so funny. So as an impatient scientist, the best thing to do is probably get into the software stuff, because then you can at least start simulating stuff. You don't have to wait for all these damn spaceships to go.
Exactly. Yeah.
That's smart. That's your shortcut. That's great.
Exactly. Yeah.
What do you program in? What is the
mostly I program in C++. Our TUDelft software is written mostly in C++.
Right.
Since already quite a few years, 4 years, maybe 5. We've had a Python interface around our software.
That's my baby now. Python. Oh my God.
I think I'm one of the few people in our team who prefers C++ over Python, but that's probably because I've been mentally formed by 15 years.
Yeah, there's a charm to C++ for sure. There's something kind of like just like old school. It feels almost, it's like you're doing all the work.
Yeah.
With C++. Although C as well. I mean, I used to, But when I was very skeptical about Python to start. I was like, oh, come on, with all this formatting and the where do you put things, and I didn't like. But wow, it is.
It's a lot easier to get into. So
I just love the packages. The packages they have is just. Although I guess C++ must have amazing packages as well. So
yes, some, but it's not nearly as good.
Really?
I think. Oh yeah.
Wow.
Yeah. Or even if the packages are good, getting the packages to work can then be a different story. Well, on Python, it's just import whatever. If that doesn't work, you first do pip install whatever, and then it just usually works.
Yeah, I couldn't get over how quickly you could develop something with Python. I mean, I'm a cheat. I use Perplexity AI and stuff to help me with the stuff, because it's one of those things that I feel like unless you're doing it all the time, I feel like I just need that reference. So it's amazing. It'll come up with stuff, and I make it explain everything to me. But it just allows you to do things very quickly. Like all those things you go like, I could press enter like 100 times. I'll just do that. That's fine. But now you go, oh no, forget that. It can write a program in a minute that will do that for you.
And then you have to debug it, get it to do what you want. But it's a very powerful tool.
Yeah, the Python stuff is just wonderful, and it seems to be one of those things that it's becoming a standard. Like it seems to be used in a lot of different things. I'll tell you, I've got a little sideline for you here. If you ever do get into Minecraft with the kid, I could see a really fun tie-in between your orbiting software and getting that to happen in Minecraft as well, because I've seen some fantastic use of like exhibiting some science. Concepts and stuff.
I might have some colleagues who I could convince to put time into linking our software with Minecraft.
It would be pretty well, just because I mean, again, it's going to suck for accuracy, but just for inspiring kids. I could just imagine to have some kind of a planetary system in Minecraft would be amazing. Yeah, I don't know what. I'm not sure what they're using.
My weekends, I think. But
yeah, there you go. Sorry. I feel like if you're a Lego fan and you've got a kid, and obviously you don't want to spend as much time. I found Minecraft was wonderful for that, I've seen. We've got a friend, James Gurney, who is building giant phages in Minecraft. So phages being the viruses that attack bacteria,
Oh wow, that's cool.
And just that kind of stuff. It's just kind of neat. So what is the focus now? What is your like day to day? What are you doing now? What is
So a part of it is preparing for JUICE. I'm the co-PI, so co-leading one of the experiments on the mission.
Right.
We'll have a series of radio telescopes on Earth that all detect the signal coming back.
How does that work? You've got multiple telescopes here.
Yeah, so the way we normally do this tracking is we have one telescope operated by NASA or ESA usually that sends up a radio signal to the spacecraft.
Right.
The spacecraft very accurately sends that signal back.
Right.
and from then comparing the signal that was sent up and the signal that comes back down.
Is that the Doppler? Using the Doppler effect?
Exactly.
Yeah. Okay.
We
Right.
measure the Doppler shift and also
Mm.
measure the range to the spacecraft and get extremely accurate measurements of the relative motion of the spacecraft.
Right.
The range is, well, down to tens of centimeters what we should get for JUICE, which is insane. The Doppler, I think, is even more bonkers. It's just that the Doppler, the range rate, essentially gives us a measure of how quickly the distance changes.
Right.
If we look at what we get already from JUICE and also from other missions, we can see averaged over 60 seconds a change in distance of 1 millimeter. So if there's some feature in the gravity field of Ganymede, the biggest moon of Jupiter, say there's a mountain on Ganymede, JUICE will fly over it, and because this mountain has mass, it attracts a spacecraft. Wow. If that mass is sufficient to pull the spacecraft 1 millimeter to the left over 60 seconds, our data will see it.
Wow.
Over 1 billion kilometers, which is, yeah. I know the data is this good. I work with these data. So it's not that I doubt that they're this quality, but just philosophically that we can.
It feels magic. It feels like magic. Yeah.
It does.
I've got a friend who's using a laser Doppler vibrometer to listen to spiders. So cool. It's actually and it's got the two beams, and one of them is sort of the baseline, and the other one is just, and they can literally pick up the movement of a spider or a spider web, and then you just get like basically a rock concert out of it. It's amazing.
And you can see how it's vibrating and get the
yeah. Awesome. Yeah. Well, because they do all these weird little dances and stuff. They've got all these weird little funky moves that they do when they're trying to mate and stuff, and so they can record all these things. And it's just, and the way they use the webs, but really, so it's just kind of fun that the same science in a way is being used to look at the very small and the very large, despite the fact that we have, different.
But it's the same kind of physical laws that are being exploited in all sorts of different directions.
So
what we do with our experiment, the Pride experiment on JUICE, instead of having one telescope measure the signal that comes in, we use a whole worldwide array of telescopes that's developed, built for radio astronomy.
Right.
And that we're also glad to get some observing time on every now and then.
Right.
And then by seeing how the signal from JUICE, what that looks like from two antennas that are very far apart, ideally on opposite sides of the Earth.
Right.
We can also see very accurately which direction the signal is coming from.
Okay. All right.
And then ideally would have many telescopes observing at the same time. And then we can complement this range and Doppler measurement, which tells us what's happening along the line of sight, but not the direction it's coming from. With our data, we can also say the direction the signal is coming from. And by combining those, then we can really get the best measurement, the best fit of how the spacecraft move, how the moons move, how the planet moves.
Wow. So, and you'll take this data, you can then put it into your software, and then you can see and you can conjecture where things are going, where they've been. Wow.
And see what are the orbits of the moons, what are the gravity fields, what are small changes in the rotation, in the tides, because it's a combination of all these things that tells you what the interior is, what the properties are of these moons. JUICE has 11 instruments, and each separate one gives you lots of cool stuff. But from just one instrument, you cannot really do all that much. My apologies to colleagues on the other instruments, but that's the way it is.
It's a combination of...
The combination, we could do so many cool things by viewing it from that direction, and that direction, that direction. We can say, okay, but this is what the interior has to be like, what the evolution has to be like to satisfy all these different measurements had.
Was it, Dominic, was it you who was saying that there are two spacecraft going out there now at the same time?
Yeah. So now there's JUICE from ESA and Europa Clipper from NASA. Both will arrive at around the same time. But
they're completely independent.
Yeah.
So, because America's got to be America. And
so that they are in principle independent, but of course when they know about each other's existence, and also now that they're launched, there is a steering committee. The first iteration I was also on to see how can these two missions collaborate.
Like work together, yeah. It just seems like a waste not to.
Yeah. Usually we don't even have one mission at Jupiter. We'll have 2.
Right.
So we're all now thinking, well, cool, but what do we do with that? Because that's.
And what do you do with it? What's the plan?
So one of the things really cool for our experiment is taking all these radio telescopes that we have and measuring how the signals from both spacecraft come in.
Right.
We can very accurately measure the relative position of the 2.
Right.
And that gives us very valuable information on the relative position of the moons and the orbital evolution of the moons.
Wow.
Because what's really cool about these 2 missions is that they focus on different targets.
Oh, good.
So they both go to Jupiter, but the Jupiter system is very big with lots of cool stuff going on.
Yeah.
The JUICE, the mission I'm working on from ESA, that will in the end focus mostly on Ganymede.
Right.
That's the biggest moon of Jupiter. It's the 3rd big one out. In the end, we'll go into orbit around Ganymede. But Europa Clipper focuses on, Europa. That's the 2nd one. That's closer to Jupiter. So there's a lot more activity on the surface.
Originally that was the one I remember hearing about first, about being potential life and all sorts of stuff.
Yeah. So one of the cool things about Europa is that its icy crust is much thinner than of Ganymede.
Right.
So it might only be tens of kilometers thick. For Ganymede, it's much thicker because it's.
I love that it's only tens of kilometers thick. Yeah. Oh, lovely, balmy weather.
Exactly. Yeah. But so by having Europa Clipper at Europa, JUICE at Ganymede, and then measuring both of them at the same time, we can get very accurate measurements of where the 2 moons are with respect to each other. And that's actually one of the things that really helps us to pin down how are these moons moving. Because I did an analysis in 2016, it was published in 2017 when I was a postdoc. I'm doing this sort of analysis, assuming we only have JUICE data.
Right.
And that turned out to be quite a mess, because then we have loads of data at Ganymede.
Right.
Almost no data at Europa, because JUICE does 2 quick flybys of Europa.
Right.
And then goes farther away. No flybys of Io. Io is the inner of the 3.
Oh, yeah, Io.
Yeah, right, and Io is really cool, but we stay far away from Io because there's a huge amount of radiation around.
Yeah.
So if we fly close to Io, all our electronics will get fried, or that's the risk, and that's the end of the mission.
Right. I'm so surprised. I'm so surprised at that. I would have thought that radiation would be an issue just all the time, but it's just the amount of it, I guess. Is that?
So the radiation is an issue all of the time. So you have to have some shielding on the spacecraft. All the electronics are in what we call a vault, which is shielded, so that most radiation doesn't go through.
Yeah.
But the closer you get to Io, the worse it gets. Because Io, it's not that we don't go there because we don't think it's cool. Io is super cool. But it's so tidally deformed by Jupiter that it's very hot. These other moons are icy. Io is not. Io is rocky.
Oh.
And it gets deformed a lot every orbit. So heated that there are huge volcanoes. Also, if you see recent pictures of Juno and another NASA mission now orbiting Jupiter, you see lava lakes on its surface.
Wow.
And some of those volcanoes spew out material so high and so fast that escapes Io, goes into orbit, into the strong magnetic field of Jupiter, and then those particles get stripped, they get ionized, and those are the particles that if they hit our spacecraft, our electronics get blown up.
God, yeah, but it'd be cool to look at, wouldn't it? I guess from a far distance, big lens. We
are going to take observations of Io.
Yeah.
With JUICE, hopefully with Clipper as well. But Juno, that's now there, is better designed to fly through stronger radiation environments.
Right. Well, it's that weird thing, isn't it? You've got to protect yourself from the radiation, but you also want the sensors to be able to do their sensing. So that's
a difficult. Yeah.
How do you do your sensing from inside a vault? It's got to be.
So you have to have then a small thing coming out to the electronics. That's one of the challenges in building these things.
Right. So here's the thing that I've always wondered about. You've got all these different missions. You've got all these different space agencies working on this stuff. Is there there must be standards for the data. Is there some kind of a format for the data? So everyone's data, is going to have certain things. I mean,
that's all. If you go back a few decades, that wasn't as good, but that's getting better and better. That there are much more stringent standards. That if you want to publish your data, and you have to as an instrument team, on repositories that are accessible for everyone. They have to adhere to certain standards. And there are still some differences. One mission might have it in one format, the other in another. But
Right, it's the format thing. Yeah.
The format thing can be a little bit different, but in the end, what's in them is the same.
Right.
And it's a matter of writing a piece of code that takes in that data format, converts it into something that, whichever software you're using can use, and then processing it. If you look at the older data, that sometimes becomes more difficult. For instance, data from the Voyager missions,
right,
still very valuable, but that's not always as easy to read. And if you go to the very old data, the 19th century data, then people writing something down. I took this observation on this location at this time.
Right.
Yeah, this time, in which times go. I mean, nowadays we have atomic clocks. That means if you measure something, you have it accurate to
they're like at sunset.
Like,
How does that help me? Yeah. It's
so
interesting. So, I guess that's just the nature of the data that you're getting. Because I know with like biotech, there's a real, one of their biggest issues right now is like when they try to get into analyzing the data, everyone keeps data in a different format. Everyone's observations are because it's not as, I guess it's not as mathematical to start off with, I suppose. But
that could be, and it's so there are still a few different file formats for the same kind of data that are used. But in the end, they encode exactly the same thing.
Right.
So if you write a piece of code, convert it to something you want to use, and then you go from there. But that does mean that the formats you want to use has to be well documented.
Right.
The further back in time you go with the data, the less well that's the case. There are stories I've heard of someone at JPL had to be taken out of retirement because they found a tape in the basement from an old mission, and no one had the faintest idea which format.
Yeah, it's like the Battlestar Galactica. It's like they got to bring back Galactica. Yeah. I mean that's going to be interesting to see, because there are definitely. I mean, I find that even just for myself, I've been doing some backup stuff, and I'm like, oh man, what do I do? I have zip drives, and I have all these formats that at the time were like wonderful leading edge stuff, and now of course it's hard to find a CD player now. Like I
think one of the advantages we have is that the amount of data we have compared to what's typical in ground-based experiments is not that big, because all the data from space missions that we get, or almost all of it, has to be sent through an antenna that's a couple meters big over 1 billion kilometers back to Earth. So the amount of data we can have just it isn't that big. Some big experiments on Earth can generate, I don't know how many.
Right. And most of it's digitized anyways, I guess, right? Most of it's
yeah.
So you've got the Jupiter mission happening. What do you have like a favorite? Are there any? What's your favorite part of it? Any favorite sensors or favorite technology? What's the?
It's something that we're working on now that I'm really excited about, is because the measurements we'll have there are going to be so insanely accurate, much more accurate than what we have now for Jupiter, much more accurate than what we've ever had for Saturn or anything else. Is that also the models we have now are just not going to be good enough anymore, because they might be able to model most of the moons to 100 meters or a kilometer accuracy, which now is fine because the data isn't good enough to get to that resolution.
Right.
From JUICE, we might go down to below a meter on how the moons move, which means that our models need to be just as good.
Right. So you got to update the software?
Yeah, so update the software, and first develop the models that we put into the software.
Right,
so
of course.
Which long-held preconceptions we have to throw away. And that might turn out to be quite a bit to go back to the drawing board and really develop new, completely consistent models.
Are there any big changes that you've come across? Is there any, like, what are there any sort of like sudden sort of paradigm shifts that you've?
So some of the really big differences is that what we do now, usually we model our models for the orbit of the moon, the rotation of the moon, and the tidal deformation of the moon.
Right.
They're partially separate. So you first compute one, then the other,
Right.
and fine. But those three have influence on each other.
Yeah.
The orbit is different, the rotation is different, and the tides are different. And then the orbit is different again. So what we're developing now is one that will do all of that in one go. That if you run your model, you're sure all of those are going to be consistent with one another. if you do that, there's various other complications that pop up. You never get anything for free. But this is all
True.
yeah. But this is always something that I've really liked. Even when I was a student, then you get a piece of theory, and then what always sort of understood it, but always frustrated me. You get all this beautiful generic theory that you can apply to model whatever you want. And I say, okay, now we simplify this. It only works in a circle. Now let's see what happens.
Right.
And that's very useful in a classroom to understand what's happening.
Right.
But I was always wanted to know, okay, but what if you don't make all those simplifications? What if you really
you just grind through all of the numbers? Yeah.
Yeah, and that's also as a student, and then later thought. Now, still, I wanted to see what if we stop using these assumptions. What if we make our model more accurate? Does that matter? Do we need it? And this is then one more step where, it's also something that's just fun, working on this with a few people to develop this, seeing where it works, where it doesn't. We have a few years till JUICE gets there, but
right.
And Europa Clipper.
And how is the computing keeping up for you? I mean, are the systems, are you able to, do you have access to powerful enough systems for this, or?
Yeah, so in general, that's holding up pretty well. Also because some of this stuff is easy to parallelize.
Oh, great.
Right. Especially now with
so you can have it running on multiple systems all over the world. And
right. Okay. There's some specific applications where the current systems, at least we have, are not suitable anymore. At JPL, they just generated a new gravity field of the moon that is so insanely accurate. The computing power they need for that is huge. I heard it was for them the biggest computing job they've done.
Wow.
And they do quite a lot of JPL.
I was going to say, they do some pretty...
Yeah. So if they say it's the biggest they've done, that's up there.
Is quantum computing going to help you on this?
That's a good question. I have no idea, to be honest.
Yeah, I'm not sure they do either. To be honest, I mean, I've spoken to. They're amazing. The stuff that they seem to be doing is extraordinary. I find it's hard to get my head around it. But it seems like this is the kind of simulation stuff that it should technically be good at.
I talked about it a couple of times with people who know a lot more about this than me, which is most people who know anything about this really. And they weren't quite able to tell me yet because the technology hadn't quite developed to the point where it might.
I feel like that's going to be one of those things. It's going to be. I feel like there's going to be like either a sudden jump, and we're going to be like, whoa, or it's going to be like a winter where it's just like, nah, I'm not getting it. You know,
like with AI, where for a while it was sort of a niche thing.
Oh my God, it was a joke for the longest time, you know?
And now it seems like half the world is sometimes running on AI.
Half.
For better or worse.
Yeah, I think you got to stick AI in front of everything you do now. That's just just going to have to be, it's got to be like JUICE AI and all that kind of, just to get people's attention, because it is extraordinary how much it comes up. I mean, I'm fascinated by it, but at the same time, I have this wonderful engineering student who does fluid dynamics is his specialty here at U of T, and he sent me a little article that Apple had done about saying like, whoa, you think you're so hot with the AI stuff. There's a few issues here that aren't, like, when it's got this weird thing where it hits a certain level of, and it just stops.
Yeah,
it won't.
So
to
me, it's sort of like fully self-driving cars,
right? Where
the first part developed insanely quickly.
Yeah.
And then on simple, predictable grid roads, I think it works fairly well. I think now if you try to have a self-driving car drive to the center of Amsterdam with pedestrians and cyclists and trams, that last bit to really get it to do what humans can do, I think that's very...
It's that 80-20 thing, isn't it? It's the same thing with accessibility. A lot of the accessibility tech is like really good, but if you've got a mouse that only works 8 out of 10 times, it's a useless mouse. Yeah. Even if it's doing amazing things with your head and tracking eyes, and if it doesn't work all the time, it's still not any use to you.
So I think AI is insanely useful. It's going to be even more useful. We also have to be careful, I think, because there's also a risk of people being less critical, of less developing critical thinking skills. So I'm also a little bit struggling how to incorporate this in education. I think many people here are, because I don't like telling students, no, you're not allowed to AI. that's forbidden, because it's also doing them a disservice when they go and graduate, go out in the world. They're going to be expected to use AI. And now someone says humans don't get it correct all the time, and that's also
neither does the AI.
No, but I think that this is also a very important thing to keep in mind when.
Look at you! You're turning into a streamer. You're checking the chats. You're like, you're gonna have a YouTube channel in no time. Yeah.
No, but when assessing how well AI works, or how well self-driving cars work, or self-flying planes, sure, they might crash every now and then. But if it reaches the point where they crash
less
often than humans, then I think there's still a whole legal, ethical debate. That's all.
Well, the other advantage of the autonomous vehicles too is that it's like if they make a mistake once, they don't do it again because they've learned. Whereas humans tend to do the same thing. They're still looking at their phones or still eating their sandwich while they're driving. And having lived in LA for a while, I'm appalled by humanity's behind the wheel, because I've seen people do their nails while they've got a sandwich and a small poodle on their lap while they're driving down the highway.
That's everywhere.
Yeah.
Looking at the chat, I see another question that I think is really cool, which is, how difficult is it to model movements of the planets or moons?
I think I can do this.
Asteroid enters close to. Excellent, cool.
Wow, it's my fancy new trick. Yeah,
I think that this is a really good question. Because in principle we can model this pretty well if we know where the asteroid is and if we know how heavy it is. Because the heavier the asteroids, the more it affects the orbits of the planets. And
how do you figure that out then? How do you figure out how heavy it is?
So you can do a bunch of things. If you have a binary asteroid, which quite a lot of asteroids are, they're sort of flying around each other, and then by seeing how quickly they fly around each other, you can see how heavy they are.
Wow.
You can say something about it if you see how big they are, you see what color they are, you get an idea what their composition is. Combined with their size, you get an idea of the mass. Or what we also do is sort of the opposite problem of this. We see when an asteroid gets close to a planet, we see how much the orbit of the planet gets deflected.
Right.
By measuring that, because we do measure very accurately how the planets move, we can deduce how much, how heavy, how much mass this asteroid has.
Right.
But the reason
you get a sense of what it's made of as well, or is there any sense of that?
So you can, if depending on if the density is low or high, you get an idea of what composition it is. But the reason why I say this is such a good question is that actually the most limiting factor in our ability to predict, for instance, the motion of the planet Mars, is that we don't know well enough where all these asteroids are and how heavy they are. So if we take the data up until now, and there's people, not me, sadly, I think it's really cool, but people who then fit all these data from planetary missions to the motion of the planets, they get a very good orbit. But then to try to propagate it forward in time, try to predict from there where will the planet be 5 years from now, 10 years from now, it's still pretty good. But if then 5-10 years later, you actually predict it to the real measurement, you see that it's sort of wobbled away right now, mostly because of these issues with the asteroids. So we don't know exactly where they are or how heavy they are.
And is there anything on the horizon for that? Any sort of solutions to that you've come up with or that are being worked on?
So there are people actively looking into this. For instance, instead of looking at each asteroid separately, what if we separate the asteroid belt into several rings of mass? Now we have less numbers in our models that we need to tweak and tune. Makes the problem a little bit easier. There are now loads of new data coming in, very accurate measurements of how asteroids move. That means we know their orbits better. It means also by looking how, not just how planets move, but also to asteroids coming close to each other. We can also see what their mass is.
Well, I guess that's a field also that I think there's going to be more interest in too, because of there's also, they're talking about mining them as well, right?
Yeah.
So maybe there's
on the one hand there's mining, on the other hand there's planetary defense. We want to know.
Oh right, yeah, that right.
The Earth.
Yeah.
And for that you need to, especially for planetary defense, you need to know very accurately how is this asteroid flying, because it might fly by very close by the Earth this year, for instance, and depending on how it flies by now, maybe 5 years later it'll hit us or not. Right. Depending exactly at which altitude and which orientation it flew by.
There's that wonderful that wonderful project that was testing how we could smack into
Yeah,
asteroids instead of
yeah,
pick them up. I thought,
yeah.
I don't know
That's
why, I just love that.
yeah,
Yeah.
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 There's another similar thing where they did this on the moon
Mm,
a while ago. Well, I think already quite some years ago, more than 10, I'm guessing,
right.
where they threw an impactor onto the moon just to see what sort of junk flew up.
Right.
And,
Right.
apparently, this was the same day or week that Obama won the Nobel Peace Prize. And there was
Oh,
John Stewart joking that he got the Nobel Peace Prize on the same day that US, bombed the moon.
on the moon.
Yeah.
Yeah. Yeah. Yeah. Well, they were talking about nuking the moon back in what was it, the 60s or
Really?
yeah, they were.
Wow.
Well, they were talking just to try, yeah, basically sort of as a show of force, and then the scientists thankfully were consulted, and they were like, yeah,
Yeah,
maybe not good,
maybe not.
not so
But,
much.
I mean, there is something to be said if you have to nuke something, better something farther away than our
Yeah.
planet.
Yeah.
Preferably not at all.
Are there?
But
What are you future wise? What are you most excited about? Are there technologies or things that you're really just? I mean, other than obviously these missions that you're working on themselves, is there any sort of scientific stuff in the horizon that you're like, wow, that I want to see what's going on with that?
so in general, what I'm really excited about is moving away from what we're doing now, typically looking at each mission and data set separately.
Mm.
We see more and more that there's interaction between them and looking at
Mm.
everything at the same time, seeing how what we study at Jupiter, how that impacts what we know at Saturn,
Mm.
finding all these data from all these different missions in one big go. And
In
in
one
general,
big open source software,
exactly,
perhaps.
exactly. Yeah, that's ideally
Yeah.
where I would go.
Right.
And I have about 30 years left.
Yeah, you got some time.
Personal
Yeah.
life, so I have some time to have fun.
Hmm.
But so in terms of the science, I'm really excited to see how much we can learn of what's under the surface of these
Right.
icy moons.
Yeah. I mean, it would be amazing, wouldn't it? I
Oh yeah,
mean,
and I mean, I don't know if I will live to see it, but after JUICE and after Europa Clipper, one of the next steps is to actually land there, and
yeah.
that can be on the moons of Jupiter, moons of Saturn,
Mm.
and to really dig into the ice and see
Mm.
with a robot or something what's underneath the crust or what is in this water.
Like what we're doing on Mars, but on
Yeah,
these.
yeah, and then also going to have to be a lot deeper because
Yeah, that's a lot of ice.
it's a lot of ice.
That's a big drill. Yeah, that's
yeah,
yeah.
although on for instance Enceladus, that's a smaller moon of Saturn,
Mm.
the ice should be a lot thinner. There's also a subsurface ocean there.
Right.
Enceladus is a lot smaller, so the ocean is thinner, and there it should be easier to drill through the ice.
I want a little underwater explorer.
Yeah,
Like, could
that
you
would be cool.
imagine just one of those wandering on a new planet on a
Yeah.
oh God, I mean terrifying, but also
Oh yeah, but so I'm not sure if I'll live to see that because that's
Right.
a lot of developments ahead. But that
Yeah.
would be
And it
be
seems to
amazing.
be. Do you find this that space? A lot of this stuff is influenced by sort of government and by the financial side of it. I mean, do you see things become popular and then get better funding and so push forward? I mean, do you think you're in a popular field?
At the moment, I think so. Now, icy moons, both on the ESA and the NASA side, are say very high on the list
They're a
of
good priority.
priorities for planetary science.
Right. Right.
Also, because it is, I think, one of or I'd say the most likely place to find life in the solar system.
Yeah, that seems to be the thing, isn't it? Yeah.
Yeah, because it's and some people say, oh, there definitely has to be life there. Others say, no, there's no chance. But I think we don't know. We know one planet where there is water, where life emerged. But what the likelihood is of that combination of water and energy and chemistry, how likely that was to lead to this, creation.
Yeah.
In however you want to define that word, that's up to you, of life. That we just don't know, and that's also I think if we say we go to Europa and Enceladus, and we find life, even if it's just very simple.
Yeah.
if we find it there, and it's basically the first two likely places to look, that means it has to be everywhere.
Yeah, I mean,
Right? That's and if we don't find it there, that means that there was something very special about our planet, and
right.
that could have been random luck on chemistry that happened to happen, or something else that's special that happened here that did not happen there.
Yeah.
But yeah, because when I talk to this to some people, they tell me, if you don't have such a strong opinion about it, that makes it less interesting. But I think it makes it more interesting. That's because we don't know
Yeah.
if it's life there. That's the whole reason to do this.
Yeah, I mean, you could go out to prove things, but at the same time, I think it's the idea of just being open to what's available is just, I mean, that's got to be. I mean, surely that's part. Well, I guess science isn't trying to working on hypothesis and stuff, but I mean, the idea that you want to just be like, well, I don't know, is there going to be life? It's exciting if there is. It's exciting if there isn't. Frankly,
to be entirely fair, there's loads of people who know a lot more about this than me. So maybe there are now developments that show now the way life probably developed here probably happened there as well. Maybe. If that's the case, if I hear that, see that, I might change my mind, but I haven't yet.
And how do you keep up to date on this stuff? I mean, what are there? I mean, are you reading journals all the time? Are you? I mean, how does one stay up to date on what's happening?
Reading journals is one important thing. ResearchGate, Google Scholar are pretty good at knowing what I like.
Right.
And also very important, going to conferences, going to project meetings, talking to people what they're working on, the ideas they have.
Right.
So it's a combination of things, and I don't have as much time to read as I would like. I know. I like reading, but I also have lots of master students, PhD students, and they read things and then show me.
Then they get to do the reading. You don't get to do the. That's the fun part for me.
It is. But
yesterday, because I did a night shoot last night. I was getting a little nap, and but I really wanted to. There was a paper that I really wanted to read, and I'd heard tale of this notebook LM where you could put in a PDF, and it would turn it into a podcast.
Oh yeah.
And I'll tell you, I was really impressed. Like, kind of terrified, but really impressed because I was just lying there trying to get a little sleep, but then I was really impressed with how they put it together. You know.
Yeah. Remember my colleague Bart, who you had on the show?
Oh yeah. Love him. Yeah.
He showed that to me.
Yeah.
And it took me a while to realize that it was AI. At some point, the way they were talking, it wasn't.
Yeah, there's that uncanny valley is still kind of there.
But it was pretty damn close.
Oh,
and I haven't tried yet. I've been meaning to, but haven't made the time. That say I throw one of my own papers in there where I should know pretty well what's in there.
Yeah.
If I then hear back that generate a podcast, if I'd say, oh no, this is completely nonsense. Sure, it sounds nice if you don't know it.
I'd love to know.
But it's just all wrong.
I'd love to know how you find that, because I mean, if you want to send me one of them, and I'll put it in mine and send you the audio thing.
I might do that at some point over the next month when the holiday starts and my agenda isn't as crazy.
Right.
This is one of the things I'm really interested in. Seeing how well this works.
It's one of the biggest issues I have with AI is it's moving so fast that I feel like by the end of the day, what you learned in the morning is already out of date. I mean, I can't, especially I've been playing with a lot of the image generation stuff and the video generation stuff, and literally within a week it's completely different from a completely different platform somewhere. So we should check and make sure that I'm having so much fun talking to you. I forgot to get to questions. So let's see what else is out there. If there's anyone in there you want to look at, nope, Agne's got some. Here we go. Okay, the wonderful Agne has been doing her homework as always, and has picked a few questions for us. Schwelmer says, "What do you think about the unknown planet far away behind the Pluto orbit, as you're working a lot of orbits of planets and moons?" The unknown planet far away behind the Pluto orbit. Wow.
Yeah, so there's this hypothesis that there's a planet 9. Planet 9 used to be Pluto, that got demoted. Now there's
Neil deGrasse Tyson. Yeah.
Now there's maybe a new planet 9. Because and I don't know all the details about this, so partially I have to speculate, but I know there's many of these trans-Neptunian objects, these objects very far away from the sun, like Pluto, but even much farther, that have very elongated orbits. So these orbits are what we call eccentric. When they're close to the sun, they get relatively close, still much farther than Pluto maybe. But on their farthest point, they're thousands of astronomical units, thousands of times farther than the Earth from the sun.
Wow. Okay.
And there seems to be something funny in how those ellipse-shaped orbits are oriented. So they don't seem to be randomly going off in any direction, but there's a clustering in a few directions that those orbits point to.
Okay.
Here, I don't know the details of why, because these sort of time spans are not my field, but that could be caused by a massive planet deep in the solar system.
Oh, wow.
We haven't seen yet, but that its gravity is pushing all those objects into these orbits. I read very recently, I think last week, that they now discovered a new object that sort of seems inconsistent with that. But yeah, if it's one object, then maybe it just happens to be on a funny orbit. You never know.
Right.
But this is also the kind of thing that with missions like JUICE and Cassini, that we can test. Because even though this planet 9 will be very far away, its signature will be very weak. The data we have is very good.
Right.
But that's also one of the things why combining all these different data sets together, I think could be valuable. That we see, okay, in the 2030s, JUICE, Europa, Clipper are there. Then if this planet 9 influences their motion of Jupiter, of the moons, it should push a little bit in that direction.
Right.
For Saturn, and Cassini was there in that direction. Mars in the 90s in another direction.
Right.
So I don't know. This is more or less my same answer as with, well, is there life on icy moons?
Right.
I don't know. Here, I think there is a lot of evidence for or against the theory. Sometimes at a conference where people are debating this, but I don't. And the people say, yes, these are there. Others say, no, they're not. If I hear their arguments, they all sound very reasonable.
Right.
But I can't put them in the right context to really properly make up my own mind. But this is one of the things where I think in the coming few decades, we can probably get more certainty, because we'll be able to model the motion of all these objects a lot better.
Add them all up together and go, oh yeah, there's something.
Yeah. And then if we don't see anything in small perturbations in orbits of things in the solar system, at some point we can basically exclude everything and conclude either no, it's not there, or see this very small, consistent wobble in orbits of planets and moons and spacecraft that concludes and say, it's probably there. And then, depending on what it should look like, we can point telescopes in that general direction, try to find out. So, can we really see anything there or not?
It is amazing that we're still fumbling around in our own solar system looking for stuff. It's amazing.
Oh, yeah. But the solar system is so amazingly big. I mean, we're used to thinking of, say, we're not talking about Jupiter a lot, that Jupiter is far away. But if you even zoom out up to the orbit of Pluto, let's count Pluto today, then even Jupiter is like a tiny little circle in the middle. Yeah. And then all these trans-Neptunian objects, if you look at all of them, then even Pluto is just a tiny little thing in the middle. So the solar system is huge, and there's so many cool, unexpected things, like Pluto, which before New Horizons went there, we all thought was sort of a boring chunk of rock.
Right.
And then New Horizons flew by, and it's really not. There's lots of activity going on in that terrain, maybe even subsurface ocean. I've heard people proposing. So even so deep in the solar system, there might be really cool things going on.
Well, yeah, and I guess this whole squishing thing is adding an element of heat that we hadn't planned on, isn't that? Or because is that a fairly new thing?
So
or am I fairly old?
Maybe both.
It's a good combo. Yeah. Don't do the math.
What's pretty cool is for Io.
Yeah.
So this closest moon of Jupiter, where there's a lot of tidal heating, this volcanic activity. Voyager observed this volcanic activity. Voyager or Pioneer, one of them.
Okay.
Observed these volcanoes, and I think it was just a few weeks before it flew by, before these data came in, that someone published a paper where they predicted there have to be volcanoes on Io due to the tidal heating. And this was in the 70s, I think.
Oh, that's got to feel good.
Yeah.
That's got to be like, yep, told you. Yeah.
right? Yeah. But especially the amount of tidal heating, and also the fact that it's not only the tidal heating. For instance, on Ganymede, which is farther out from Jupiter, tidal heating is only a fairly small part of the total heat budget, but it's the heat of its creation that's still in there, heat of radioactive decay in its core that's keeping it hot. Plus, also the fact that once you have an ocean, it's very difficult to freeze it, because when an ocean gets very thin, then you do have the tidal heating in the ocean itself, not in the ice, but in the water. If the ocean becomes very thin, you get certain standing waves in the ocean that heat it up, and that then might help remelt it. So, freezing an ocean once it's there probably is pretty difficult.
Right. Whereas we used to think, oh, it's freezing cold, nothing can be, it's got to be solid.
Yeah.
Right.
Yeah. And still, for instance, for a moon like Enceladus, which is very small, it's just a few hundred kilometers compared to our moon. It's, I think, 1,700 kilometers. It's really small. It's not that super close to Saturn. So, but before observing it with Cassini, we thought, well, it's not that interesting. But there's a subsurface water ocean. There's lots of tidal heating. There is still the question, there's now starting to be some theories that resolve that. But how can it be that such a small body can undergo so much tidal heating? It's probably because we don't understand yet that well.
Right, we're missing something.
That's going on in the interior.
Right.
And now there's the idea that there's sort of a sponge-like structure in the interior, and that squeezing that sponge-like structure causes a lot more heating than we thought.
So what it's made of is going to adjust how much heat it's going to create when it's of course.
Yeah,
right.
Absolutely.
I see Janelle's got a good question. Why don't I do my little thing? And
that's sort of, we got started on that, but then
I squirreled.
We went off on some little tangents.
I told you, a bag of squirrels right here. Right here. Yeah.
So I started studying physics for a year. Like I said, then thought, this isn't for me. I'll move to aerospace engineering, which I always thought space was really cool. I thought I wanted to do this. But then
did you want to go to space originally?
Oh no, I'm very happy staying here on the ground.
Me too.
And having
robots.
All the room in the world. Loads of respect for people who do.
Yeah, me too.
But
not for me. Yeah.
But then I was doing my bachelor's, and then to be honest, I got a little bit disillusioned with space, because one of the things I liked in my education was math and big complex models. And from the picture I got initially, there wasn't that much like that in space science. Not true, just my wrong idea.
Right.
But I got lots of course in aerodynamics. I thought, aerodynamics, this is cool. Lots of cool equations of airflow. So I decided, no, I'll go do my master's in aerodynamics and do, whatever in that direction.
Right.
And then I had a bachelor final thesis, which here in Delft is a 10-week project with 10 students that you work full-time on a design problem, and then you can rank your preferred topics.
Right.
I thought, number 3, let's put a space project. Who knows?
Right.
And indeed, I got that third topic, and that was so cool. We designed a mission to compete in the Google Lunar X Prize. Was a prize to design a private mission to go to the moon. Oh, wow. Going through that whole process, even if it's small, in 10 weeks. How do you build and design a space mission? Wow. That whole process was so cool to me. I thought, no, I have no idea if there are going to be jobs in this, if this is for me, but this is so cool. I want to try.
Yeah, I will make a job.
Exactly. Yeah.
And how hard was it to find? You've obviously found your place. How difficult was that?
So, a part of it is working hard, and a part of it is also being in the right place at the right time.
Right. Which is the Netherlands, by the way.
Yes. I was
That's what Agda keeps telling me. So,
So I'm very happy to be here. I did a short postdoc in the north of the country. Spent a little bit of time in Germany.
Right.
Most was able to stay here.
Right.
Some people love to move around the whole world. I'm maybe a little bit less adventurous.
Right.
I prefer to stay here.
I like home. I'm a big fan of home.
Me too. Yeah. But also I think if I would have to give advice to people looking for a career in this direction, is to not be too specific on the details of it. I did my master's thesis on optimizing re-entry vehicles, optimizing their shape that they would perform the best entering into the atmosphere.
Wow. Oh, that's got to be
also
cool.
really cool. That also
Yeah.
I chose that topic.
You're designing spaceships, for God's sake.
Yeah, exactly.
Yeah.
I like this aerodynamic stuff. I want to keep doing this. And so one of my supervisors from bachelor thesis was an expert. It is an expert on reentry. He still is. And he said, "Oh, no, come study with me. You can do space and aerodynamics at the same time."
Right.
I didn't do much aerodynamics, but he only told me that later.
Right. Right.
But then I moved there. And then there was a PhD position that opened up here using laser ranging over interplanetary distances for position determination.
You had me at lasers.
Yeah. And so the weird thing is I took for our curriculum, most of the courses there were because I thought they were cool. I didn't take planetary science. I didn't take satellite orbit determination just because they didn't fit my schedule.
Right.
In the end, I chose a PhD direction that combines planetary science and satellite orbit determination. And it took me some time to get up to speed with all the material, all the theory. But I thought it was a really cool topic. And I thought that the challenges in that project were things that I could learn from, that I would be good at. So I decided, okay, I'll go in that direction.
Wow.
And that ended up being a really good choice because now 15 years later, I still, among others, work with the people I met in that project.
Oh, wow. Okay.
And still work on, not laser so much anymore, but still motion in the solar system.
Right, right.
I started that there. And probably if there would have been a different opportunity for a different direction to specialize in, I would have had great fun. Hopefully have been good at it. But I think that's important to not already in advance have so much of an idea, okay, I want to do that specific job.
So be open to the opportunities as they come up.
Exactly. Yeah.
Right.
Yeah.
Right. No, that's good advice. Very good advice. And what kind? Someone was asking about what kind of math you were using. What branch of mathematics? There you go. Let's have a look at this.
Oh yeah. So mostly that's a calculus analysis. So it's not if I talk to quote unquote proper mathematicians.
Right. You're not talking to one right now. So
good. Then also, what I do is not proper mathematics, but it's very applied mathematics. How do we model something? It's setting up what we call differential equations that describe how things change in time,
right?
And then finding good ways to solve those equations, because it's one way to set them up. It's another way to say, okay, if this is the equation, what does that mean for how the orbit of a planet really moves? So I do sometimes wish that I had more chance to dive into some more areas of mathematics that I don't know that well, because I do think that is really, really cool. But
there's just not enough hours in the day, I guess. Really,
exactly. No. There's too many cool things to do.
But you don't feel limited by what you're doing now.
Oh no.
Just by the time of just literally the hours of the day.
Yeah.
Okay,
and also think that if I'm at a point where I have more time to work than ideas to work on, that's a sign that I should choose a different job.
Right. Very good.
Give me 10 master, PhD candidates, postdocs, whatever.
Yeah.
I'll come up with 10 cool projects.
Yeah.
At some point, I just won't have time to advise them properly. But no, there's even in my field, which in my view is very big because there's so much to do.
Yeah.
But still, out of the whole field, it's just a tiny niche. And there's so many things to do, so many directions to go in.
Right.
I'm not by no means limited.
You're never bored.
Oh no, never.
All right, so because we got here. I've got some Agni questions. How about this? You don't have to say Stargate, by the way, just before I say this. But what is your least favorite sci-fi movie? And are there any that depict science that you work with better than others? Are there any? Are you a sci-fi fan?
Oh yeah. So I
kind of have to be, don't you? I mean,
also so there are some colleagues of mine who aren't, but they are in a minority,
and they're very unpopular.
Oh yeah. I have an ongoing feud with one of my colleagues on whether Star Trek or Star Wars is better.
Oh boy,
that's a strong opinion. Yeah,
well, they're different. One of them is science fantasy, and one of them is science fiction. I mean,
true, but it's also just fun, especially with him, to argue about this. Yeah. That's half fun. But I've always been a very big Star Trek fan.
Yeah.
So I don't know what my favorite movie would be, But I grew up watching Star Trek: The Next Generation.
Right.
And
TNG, that was mine
that's
too. Yeah.
it's we still rewatch it every now and then.
Yeah.
And it's compared to what comes out now, I'm going to sound very old, but compared to TV that comes out now, it all goes pretty slow. There's some huge disaster, the world's on fire. What do? We'll go have a calm meeting and talk about it and see how we can resolve the situation.
Right. Yeah.
This also, I mean, when I was watching it, I didn't really realize that appealed to me.
Yeah.
But now thinking back and now rewatching it, I also think that that's nice, that they have a big problem, and the first thing they do is sit and think, what are we going to do?
Yeah, TNG is almost more speculative science fiction, isn't it? It feels like they're trying to work stuff out in the stories, whereas Star Wars, I feel like you're enjoying it. Not to diminish it. I was a huge Star Wars fan, obviously, but I feel like Star Trek inspired me into science and Star Wars into fiction, if that makes sense.
Oh yeah, I get that. Yeah, and Star Wars is more adventure. And it does that a lot better than the Star Trek does.
Yeah. Although there's some pretty exciting. I remember everyone complaining about the first Star Trek movie and saying it was boring, but I remember being blown away by that. I was like, it's our spaceship. Like I remember just being so enamored with that as a concept that this thing could come back knowing everything and saying like, hey, always intrigued me. That was,
the Star Trek movie that I probably have the fondest memory of is First Contact.
Right.
Which was I was 13, 14 when it came out, and it was also fun and lots of action, lots happened. Maybe not the typical Star Trek, but I remember renting that on video when it came out.
Yeah.
And just watching it on repeat between getting it and having to
send it back. Yeah. Back in those video store days.
Oh yeah.
No, I actually I remember going to see that first original Star Trek movie in the theater, and just I couldn't get over it. Just couldn't get over it.
Yeah, I'll move a little bit.
You're blinded? You're being blinded?
Yeah, a little bit.
All right. So, are there any films or TV shows that you go, wow, that's it. That seems, any ones that you feel like the science is a little more accurate than others?
On TV shows or movies, I'm not sure. I have to think about that. But what does come to mind very quickly is a series of books by Kim Stanley Robinson.
Oh yeah,
the Mars trilogy.
Yeah, it's fantastic, isn't it?
It's for those people who don't know it. It's a few hundred years of following colonization of Mars, going from the first people, or almost the first people landing, to a thriving ecosphere society there.
I think I've only read the first one. I gotta
get. So it can go a little bit slow because the author likes rocks and geology, and there's 20 pages on. Look, here's a rock, very nice rock. There's another rock. Also a very nice
Maybe
rock.
Don't write that in the review.
No, so you have to sort of go through that, but
right.
And they do sort of squeeze the terraforming time scale. It's sort of done in decades or centuries rather than millennia or tens of millennia.
Right.
But what it gets really right, which I love, is that going to another planet, then people go there to terraform, to change the planet to live there. But living on that planet then also changes the people who live there. And he really describes, I think, amazingly, Kim Stanley Robinson, this author, how this interaction goes, and how by living on a different planet, you get a whole different society of humans living there.
It's the thing I loved about The Expanse as well, was the idea that they became these different. They were different people, basically.
And so the one of the reasons I sort of have to think about which TV show or movie gets the science right is that I try not to think about that too much, because if I do, all I'll do is be annoyed at this is wrong, that is wrong, that is wrong.
Yeah, try doing it with acting. I'm always like, oh, what?
Yeah.
I didn't believe, So I tried. It's always, to me, it's the greatest compliment to a film when it's over and I go, wow, like you just sort of forgot to examine it as a film. There's just very few that'll do that. Oh, it's funny. So I guess we can probably blame the Mars series for Musk wanting to go there. I'm
Oh,
guessing. It's
quite
got to
possibly.
be. Yeah,
Yeah,
it's got to
yeah,
be. I feel like that must have been. I read the first one and I was just absolutely blown away. As
yeah.
always, there's just so many things to. I'm now reading this one called. I've started numerous times and I'm determined to get through it this time. Ancillary Justice, which is fascinating. This concept that the spaceships and the people on it are basically the same thing. So they all experience. They are the spaceship looking down at the planet. They are also the people on the
Huh.
spaceship. They are also, so they have a sense of, there's a plurality to them all. And then what happens when one of those ships gets destroyed, and this part of a huge thing becomes a
Oh, yeah.
singular. Yeah,
I have it at home. I have it on my far too big
I
um,
know the stack of to
pile.
read.
It's at the moment. I think I'm reading things as quickly as I am buying new things.
Yeah, yeah. I think I
Uh,
buy them faster than I read them at this point.
yeah,
But
it's
I'm that's why I'm a huge fan of Kindle, because first off, I love looking things up. Like if there's a word that I'm not entirely sure of, I hate reading over it. I have to know. It's like pathological. I have to know. So I love being able to tap it and look things up and then explore from there. But also it means that I can bounce from book to book.
yeah.
But
But
yeah,
so I think if I could go into the book and click something and look things up, I'd be 2 pages into a book and down a Wikipedia rabbit hole and
yeah, I'm
not
not
get
so
back
good
to
at
the
that.
book.
It's true. It's true. But still, it's all part of that. Yeah. I mean,
Yeah,
yes,
yeah,
I've also discovered that I have to read during the day now because I was only reading at night. So I never got anything finished because always falling asleep. I have to read things over and over again
oh
because
yeah,
your eyes are
yeah.
crossing because you're tired. And yeah, so I've started actually
Yeah,
putting time aside in the day to do some reading because I
yeah,
feel like,
that's also why I don't like to read just before I fall asleep, because then I
yeah,
get exactly this and then I get
yeah.
confused.
Yeah, I have to go back and read the same chapter over and over again. It's yeah. Okay, if you had, this is a good question. If you had infinite money, what kind of mission would you build and where would you go?
Huh. If I had infinite money,
I think this is an
what?
Agne question. This is
Huh.
good.
If I had infinite money, I wouldn't build one. I would build many different ones.
Right.
I think that's like I said, for Juice, we have from one instrument you can get a lot of information, but you can't really dive into the deep questions.
Yeah.
The same if you really want to understand very well what's going on in the solar system or beyond,
Mm,
you have to look at many different things.
right.
I think that one aspect which is not something I know too much about. I'm saying that a lot. Maybe now people think this guy doesn't know anything, but it's
No,
just a
I've
lot.
noticed this, that the more you know, the more you tell
Yeah,
people how little you know. That's
yeah,
it's good. It's good.
yeah.
It's good. Yeah.
But so I think there's really a lot of potential in comparing exoplanets to solar system planets.
Mm,
I think building really big observatories, probably in space, to try to image exoplanets.
mm,
I think there's a lot of potential to learn things, because I mean we have 8, 9, 10, depending who you believe or which
mm,
definition you use,
right.
planets in the solar system. There's uncountable planets in other
Yeah.
solar systems, thousands, maybe more now that we've detected,
Mm,
and we see them being on a much wider range of orbits, conditions than we see here. So
mm.
our solar system seems to be pretty boring in a way that we don't have these planets orbiting super close to the sun that are thousands of degrees hot.
Right.
But those
Right.
are around other stars. And I
Probably a
think,
good thing for our
yeah,
survival to some extent.
probably,
But
yeah.
yeah.
Maybe
Yeah.
that's one of the reasons why there's life here and not there. If there would be
Yeah.
such a planet
Yeah.
here, we would never have existed.
Mm.
I think that's one of the things
So
that.
you would do multiple missions. You'd send
Oh yeah,
them off everywhere, right?
yeah,
Okay.
yeah, yeah.
But you would stay at home
Oh
and
yeah,
track
I'd
them all.
happily to stay here at home where I like
Yeah,
it.
yeah, that's good. So that's interesting. So it's not so much about where you'd go as the information you would get from these things. That's fantastic. Yeah. All right. Are you okay for a couple more questions? Is that?
Oh yeah,
Yeah.
sure. Just a little bit of a dry throat. So I'm
Oh
talking.
yeah. Sure. Okay, great. Okay. Any surprising or weird findings in the legacy of data in the 19th century? When you looked back, were there any things you went like, what?
So no, not that much. That would be cool if you can find a data set and you see, oh, what the hell is this? But there is a really cool example here that I'm not sure I don't think it was data from the 19th century, although some of it might have been involved in there. That for a while there were some people, not too many, but some serious scientists, I think in Russia, who were convinced that Phobos, the moon of Mars, was hollow, that it was basically created. Because
that it was like it was designed.
Yeah, because what happened is, I think also using this old data for Phobos, they saw that the orbit of Phobos is drifting, just like the moon's orbit is moving away from us. Phobos' orbit is moving toward Mars, where in 70, 80, 90 million years it'll be destroyed. But at the moment we see it getting closer to Mars, and there's two ways in which that can happen. One of them at the time people didn't realize. One is these tides on Mars, that if you're far away from Mars, the moon moves away. If you're close enough to Mars, the moon moves towards you.
Pulls
I'm
towards
happy
it, right.
to talk for half an hour, draw diagrams on why that is, but I'll spare your listeners those details. But the other thing that gives, if you look at the orbit, almost exactly the same effect is atmospheric drag. If you have a spacecraft in orbit around the Earth that's a few hundred kilometers up, it'll slowly get closer and closer and closer to Earth.
Right. Like the ball going towards the center.
Exactly, because even a few hundred kilometers up at Earth, there's almost no air, there's almost no atmosphere, but there's a little bit, and spacecraft go really fast, so they slowly lose altitude due to drag.
Right.
So what happened with Phobos is people saw its orbit was going closer and closer and closer and closer, and they concluded this is due to atmospheric drag. And then they did the calculation and said, well, but for this to be due to drag, Phobos has to be super light. There's no way Phobos can be a solid thing. So the conclusion was Phobos is just a thin shell.
Wow.
It has to be created.
So they jumped straight to aliens. That seems like a rather unscientific approach.
So if they jumped straight to aliens, that I'm not sure.
Yeah.
But probably some people did.
I would love it to be true, but
definitely.
So that's fun. So the Russians were playing around with hollow moons as an idea.
And I think this was a Russian scientist. I don't remember the name.
Yeah.
And I'm not sure how long and how seriously this was considered, but I think I do know for a while this was a thing that was put out there, like, hey, could this be explanation for a thing that we see? Which in the end turned out to be something very well known: the tides that are pulling Phobos closer and closer to Mars.
Way to go. Science, once again, taking all the magic out of the...
Can I give another example of a cool progression in understanding, which is again on Enceladus, this small moon of Saturn, where when we first observed it, well, it was just a moon orbiting Saturn. Well, okay, boring. Well, not boring, but just a moon. There's lots of moons. Saturn has, I think, 100 by now, so whatever.
Yeah.
Then I think Voyager flew by, and we saw that it was pretty light. That the Voyager, maybe already knew that, but that was clear. Enceladus is very white. It's odd. It's a lot whiter. It reflects more light than most moons, but okay, sure, interesting. Then Cassini came, and that showed that the surface has all these sort of funny stripes, these features that show that the surface is very, very new, which is weird because such a small moon shouldn't have any activity.
Right.
Okay, that's funny. Then they saw these plumes, because Enceladus has these cryovolcanoes, I think they're called, where water is pushed through the surface as a geyser so high that it goes into orbit around Saturn.
Wow.
And that's actually formed one of the rings.
Oh,
and
right.
Then,
okay. All right.
And then what the Cassini team did something quite extraordinary. They changed the orbit of the Cassini spacecraft to fly by Enceladus more often. And then there was a whole series of measurements where our understanding of Enceladus kept on changing. First, the idea was, okay, so we fly by Enceladus, we measure how Cassini moves with these Doppler measurements, get a gravity field of Enceladus, and then the first conclusion was there is a subsurface ocean like on Europa, but only at the South Pole. So it doesn't go all the way around. Like
wow, okay.
Only at the South Pole, which matches because there were these plumes at the South Pole. So okay, that was known, that was done. Then some people reanalyzed the data with some other methods, and they concluded, sure, that's possible, but it could also be the whole moon. If you take into account some more models, both scenarios are consistent with the data. And then there came another data set, which was not the radio tracking, but the camera images of Enceladus. And that showed what we call a libration. which is the shell, so the outside of Enceladus wobbling back and forth,
Oh, wow.
which is something we'd expect due to the interaction with Saturn.
Hmm.
But the size of this wobble was so big that the conclusion was the ocean has to be global.
Right.
Because if
Right.
the ocean is global, if the ocean is on the entire interior, that
Hmm.
means the outside of the moon is what we call decoupled from the interior. So the
Right.
outside rotates separately from the interior.
Right.
And that's the only way that we could explain, I didn't do it, they could
Right.
explain these big wobbles in the rotation of Enceladus. So I think it's a
Wow.
really cool example of where basically at every step, the scientists take the data they have,
Hmm.
come to a conclusion, but also every time with a note, well, this is based on our data and models now. And
Hmm.
every couple of years, someone comes, nope, probably this, nope, probably this, nope,
Right.
probably this. And this gets refined to a point where we viewed it from multiple directions. And now we think we know what's going on, more or
Right.
less.
Right. Until we get another pass on something.
Yeah, so also I think when Juice and Clipper get to Jupiter, who knows what sort of long-held notions of the moons of Jupiter
Right.
will be proven untrue.
Do you find yourself? I mean, do you if something gets disproven? Do you find yourself? Are you excited about that, or do you go like, ah, crap? Now I gotta rethink everything, or
So ideally, it'll be the first, and I think
right?
in the long run, it'll be the first. If it's something that I've worked on a lot,
Hmm.
and then the conclusion is, nope, sorry, it's not true,
Hmm.
I'd probably be bummed out for a
Right.
while.
Right. Even though
But
you
that's
have made progress and that you've
sure,
discovered that it's
yeah.
not the case, but yeah,
There's also something that I always tell my students, that a negative result is also a result. It can be a very
yeah,
important result.
yeah. I used to tell the
Uh,
tech bandits, when they got it right, I would say like, God damn it, we got it right. We didn't learn anything,
yeah,
you know.
yeah.
So it worked. Shoot.
But there
So,
was recently from the data from Juno that flew by Io
hmm.
that proved that, again, through looking at tides, tides are really cool. You can see a lot of things with them.
Hmm.
Looking at the tides of Io, measuring those with Juno while flying by it, they concluded there is no magma ocean under Io's surface because these other moons have water oceans under their surfaces.
Hmm.
For Io, there was the hypothesis that maybe there under its surface there's a layer of magma
Yeah.
ocean.
Yeah.
Juno now showed, nope, that's not the case. The measurements are not consistent with that.
Right.
I know some people were a little bit bummed out by that because
Yeah.
they worked a lot on modeling these oceans, and that's not to say that those models are worthless because they still tell us various other things.
Hmm.
And I know some other people were very happy because they were already of the opinion, yeah, no, it doesn't have a magma ocean, and they were right.
Right. Oh my God. It's just I just can't imagine. Like, it's just, I think it's kind of a mindset, isn't it? You just got to have this mindset for just wanting the knowledge, not the glory, if that makes sense.
So that's definitely one thing of it. There's also another, before I do myself too much justice, that because there are some people in this field, to a certain extent, who are mainly motivated in doing their work by answering these ultimate questions. Knowing, okay, how big is the subsurface ocean on Europa? What is the temperature in Io's interior? And that's also part of my motivation. Another part of my motivation is that the work to answer those questions, I really like doing that work. I really like building these models. I like analyzing those data, getting everything to work like it should.
I get the sense.
So
I get the sense that you almost prefer the numbers to the photos. You know, like you almost.
there's probably quite a bit of truth in that. Yeah.
Yeah.
I have some colleagues who come from a background in geology, and having watched The Big Bang Theory, I like to make a little bit of fun of them. But so, and it's not that before all the geologists get angry, it's not that I don't think geology is a proper science, but it's not the kind of science that I can do.
Right.
Because there's so much interpretation in that, and if I can do it with numbers, then it's easier to know yes or no, or yes within these bounds, or within these mathematical assumptions.
So biology would drive you nuts then.
Oh yeah. That's too dirty and squishy and vague.
Yeah, I had no interest in the squishy stuff before, and now I'm coming around to it because I feel like there's some fun robotics, and obviously the whole CRISPR Cas9 stuff is is fascinating as well. But yeah, the data. If you're into the data, it's a
Yeah.
squishy data is not.
Yeah, no. So and also maybe related to that, I should not get too close to hardware. Don't ask me to build something. It's great that others do.
Yeah.
If they don't, then I cannot do anything.
Right.
But I should.
But you're building Lego. You say you're a Lego fan.
Oh yeah, sure. But then there's nice books with clear instructions.
Instructions, yeah. That's true.
I do like then taking it apart and building random new things.
Yeah, that was always my thing.
Yeah.
I feel like it's very easy to get caught up in the perfection of it. Like, oh, there it is. Now it must be preserved, and But I love the idea of just these the random things.
Luckily, I have a 4-year-old, so her
Legos
don't stay intact.
You'll get plenty of random then. Don't worry about that. Yeah. And what are they into? What's the? You get a sense of are they sciencey? Are they artsy? Where do you see it?
She's 4 now, so when you ask her what she wants to be, she sort of goes from one to the other. Sometimes she wants to be an astronaut. The rest of the time she wants to be a unicorn princess.
Oh well, so it's hard to choose. It's
exactly.
Hard. Yeah. Baz was wanted to be a chef astronaut, and I was like, well, that's interesting. Yeah. He's like, I like space and I like eating. That's a good combo.
Awesome.
Yeah, and he goes into sports management, so it's it's just kind of fun to see. I love one of the great things about being a parent. I found was I was always sort of scared that when you were a parent, you means you had to be a grown up. And the reality is, being a parent, you actually get to be a kid again. Like, there's so many things you get to, explore again and see through those.
You get to play. I was with my daughter as a family at some playgrounds this weekend. And then, even though you're supposed to be a grown up, you can still go in the swing and go wee.
Right? Yeah.
If you have a 4-year-old with you, suddenly that's not weird anymore.
You got to be careful though. Once they're no longer 4, it is weird. So you gotta move on.
But I think the good thing is that they'll tell you, Dad.
Star Pilot 6 has a good quote here. Says that I believe they will both come to need both chef astronauts and unicorn princess.
Exactly. Sure. There we go.
And I love that there's there are. I think the thing that frustrated me growing up was that as soon as you were in the arts, it was like the screen. This is the art side. That was the science side. Yeah. And I feel like you miss so much because of that. Because I always loved the science. I always was interested and fascinated. I was terrible at school, but I loved all the reading and the research and just trying to get my head around this stuff. But because I was in, theater, it was seen as like, oh, well, so you go do art stuff.
Yeah.
And I love that now. And I think a big part of it is just people knowing that there are these other types of jobs out there. It used to be like you're astronaut, fireman, doctor, lawyer, and that's basically your, and everyone had, or you were going to be a sports star or a rock star or a movie star, whereas now there's this wonderful sort of access to all these different, jobs that people just didn't even know existed. But it is amazing how few of them they know about anyways. Like, there's an organization I work with here called Let's Talk Science. Well, whenever I can, I work with them. And one of their big things is like, you can't become, an orbital specialist without knowing that there's such thing as someone who's, who does that. So a big part of it is telling the kids what these jobs are out there. Do you do much outreach for your stuff? Is there a lot of that or
some? Yes. So I quite often go to observatories or other places where they invite me to give a public talk. Usually that's on JUICE. I go tomorrow.
Oh, really? Oh, fantastic.
Yeah.
Are these things that we can see? Are these presentations that are webcast or anything? Or
they sometimes record them.
Yeah.
Sometimes are webcasts, but they are in Dutch. So I think that's where sort of
that's what Google translates
the audience to the size of a post stamp on the map.
Right. Okay. All right. Very good. And how many languages do you speak?
2. So the Dutch and English. I had 6 in school. And the other 4 went poof. That's which
I have 3 passports in 1 language.
Oh, well
I suck. Like it's like we're supposed to know French as well, but it's so terrible. My French is so. I would start a war if I tried speaking it.
This I think also professionally one of my main things I wish I would have learned better is French and German.
Really?
In principle, the field is all in English, and speaking just English can get around just fine. But there's loads of cool stuff going on in France, loads of cool stuff going on in Germany, or French-speaking, German-speaking countries. And it would be nice to be able to switch to different languages.
That's where the communicator comes in. That's where the Star Trek translator,
yeah, I think we're getting pretty close.
We're getting really close. I'm sort of being silly, but I'm also not. I think that, could you imagine a world where we can just all understand each other? I think that's
if we have now a meeting with Microsoft Teams or something, there's an option to transcribe the meeting. It does amazingly at just picking up the things that are spoken, picking up different voices, who's saying what, making a transcript. Probably you throw that into ChatGPT or whatever, say, translate this into whatever language you want, and then speak it out loud.
It's amazing.
To be honest, I'm a little surprised that no one, or maybe they have it just no one that has built an app or a tool that basically works as a universal translator. Because
I think they're definitely trying it. I think I guess it seems to be like it's like English French or English German or whatever. Or like it tends to be like they stick to a couple of languages to keep it down. But Google's always been pretty good. Although there's a few things that are kind of that it does some funny things once in a while. But I've had chats like there's a guy who I talk to in Italy every so often. And I don't speak a word of Italian. And so it's just Google. It was just Google Chat. And it was sort of amazing. Well, once I figured out that I had it set on Spanish, then it made a lot more sense to them. but yeah, it was amazing how much you could get by. And apparently some of the AI pins, those sort of the ones that you can wear and stuff, are getting better at it. But yeah, that's cool. I just cannot wait. I wish I had a Star Trek translator because I only understand German and very little English. Yeah, wow.
That's coming, I think.
Yeah, I managed to fail German as well, which basically I failed a vocabulary test in German, and it's all how it sounds. So I don't know.
So I got barely passing grades for German, and apologies to my German friends, colleagues. German is almost just a funny accent of Dutch. They'll say it's the other way around, but it's not. And even then, I managed to fail it.
Does the Netherlands have a history of space exploration or why it just feels like it's there's so much going on there, and it's not a place that I would have immediately thought of as
one really good thing for us is that the biggest center of the European Space Agency is in the Netherlands. ESTEC, so more or less the JPL or NASA Goddard of Europe, is in the Netherlands, and there's a lot of activity around there, lots of companies.
So that makes it a priority for people there. Yeah. Okay.
And also the university here where I work in Delft has one of the few in Europe dedicated aerospace engineering faculties. In most places, aerospace is a specialization of mechanical engineering. Here it's its own dedicated thing. So there is a lot of things going on here. Partially, I think that is just because of luck that we have a few really good places that happen to be located here. Of course, if you go back much farther in time, we had Christian Huygens, a Dutch scientist, who was the first to see the rings of Saturn, I think.
Oh, wow.
One of the very early developers, adopters of optical telescopes. And at the time, the 17th century, we also had a very thriving academic environment. I recently read a book on Dutch history, which was funny that some of the things going on then was the same they were going on now. There were lots of foreign students, foreign staff, which was quite unusual at the time. And one thing I thought was hilarious, that there was a French professor in the 17th century here who thought his work was great, the environment was great, but the food was horrible and the weather was horrible. 300 years later, people are still complaining about the exact same thing.
What is the food? What is I've never been there. What are you known for?
Nothing.
Oh, okay.
The Dutch food is very impressive in the sense that for a long time, the Dutch colonial empire controlled the spice trade in the world.
Right.
Not a single one of those spices managed to find its way
into your food.
Maybe now some of my Dutch friends and colleagues will say, no, there's a lot of good Dutch cuisine. Sure, there's some of it. But in general, Dutch food is seen as fuel. Yeah,
Right.
see, pickled herring.
Is it really pickled herring? And look, I love pickled herring and I love Edam. So
Well,
yeah.
I like Dutch cheese.
Mm.
Pickled herring, not so much.
I mean, in small doses. I don't want to eat that every day,
Yeah.
but yeah. No, I'm a fan of the pickled fish. I've got to say,
Ah.
Although my dad, his first apartment in London, England, was above a jellied eel factory.
Oh,
which
wonderful.
is a concept that I just cannot get my head around at all, or my taste buds. Look, I shouldn't keep. I know you've got a 4-year-old that's going to be so much fun to go and see, I'm sure. So I shouldn't tie you up anymore. Dominic, thank you so much for doing this. It's such a pleasure to talk to you. And we've only kind of scratched the surface because there's all.
I feel like we could go on for a few hours, but
oh my God, easily. But you've got a life. I may not, but you do. Is there a way? Are you? Could people reach out to you? How do people keep track of what you're doing? How do you use social media at all?
Not near as much as I should probably, but I'm on LinkedIn.
Right. Okay.
Right. I'm very old-fashioned. I remember MySpace and MSN Messenger.
I remember MySpace. Oh yeah.
But I'm on LinkedIn. I'm on ResearchGate for the real people.
Is ResearchGate? Is there a social aspect to ResearchGate? I don't think I've ever played with
a small one, but it's not. It's mostly a way for people to share their work. There are some chat functions, but mostly it's a way to share papers, share what you're doing.
I should start using that more then, because that just seems like a good. I'm constantly coming up against paywalls for all the documents that I.
Yeah. So if you go to Archive or ResearchGate, many people post their stuff there.
As well as where that.
Or some other websites which probably should not be named.
Oh really?
Oh yeah.
We'll get them off. We'll get them off. We're not streaming.
Okay. I always write in. Oh, maybe I shouldn't say this too loudly. Sometimes write on big letters on the blackboard some names of websites that students should not visit because they're illegal, and then I leave it to them to decide whether or not they should visit there.
I'm so torn on that, because you want to fund, you want to support the people who are writing these things, but at the same time, you can't afford hundreds and hundreds of dollars worth of research books.
And I mean, for books, sure, but books are a different story. There, people put in a lot of work, also get paid to write those books.
Mm-hmm.
But papers, I mean, I don't get paid to write a paper.
It's a weird system. It's a very weird. It feels wrong. Somehow.
Yeah, it does. And publishers make a lot of money. I mean, publishers are important. They do have an important role. But the fact that we are all allowed to put our paper openly for free on ResearchGate, on Archive, wherever we want.
And that's a relatively new thing, isn't it? It used to be you had to have them. Do you still have to have them published to be this? There's still procedures for this stuff that involve paid publication things, aren't there?
No, so we, in some cases, we have to pay to publish in a certain journal,
which is insane to me. Let me do all the work and then pay you to use it.
I mean, also, that those publishers have operating costs they need to cover.
Whatever.
But I think the amount of money we pay for them, I think, covers that.
Yeah, you
well, and then some.
Is this something the government should be looking after? Do you think? Is this something that should just be open?
So I think that some of the things that are happening now is that people in the scientific community are organizing themselves and setting up their own journals, and then they do all the work themselves. Then the cost, what you pay to publish in there, is indeed to cover the costs.
And that's still seen as legitimate to the community for the. Okay, all right. Well, good. Yeah. It seems like a strange. It's very. It's always one of those things that it's been very.
It is, to me. But I think it's a system that's very difficult to tackle, because we are all, as academics, also required to publish.
Yeah.
And then if we choose to only publish in journals that are entirely open access or as free as they can be, yeah, in some cases that means you don't publish in the top tier journals in your fields. You don't get promoted as much. So there's a lot
So like being in Nature magazine or something like that is going to have a more cachet to something. Yeah. Okay. I guess that makes sense.
And what you need to, I think, to overcome this is to have something in place that is seen as equally good. But to have this in place, you first need to have it be equally good, have as many good papers published there. And there's a lot of incentive not to. But I do see the community moving in that direction, like in software like in data, a lot more now is open source than it was
Yeah, it
10,
is.
20 years ago.
Yeah,
So
and I can
it's
often
really
find
good
stuff
direction.
if I look long enough, I can usually find something that will at least explain most of what I'm doing. For the most part, the abstract is enough for me. Anything
Yeah.
else becomes a bit, you know, I just pretend to be smart on television. So, you only got me for so much. Well, look, again, Dominic, thank you so much. People can look for you on LinkedIn. Obviously, Tough Delft. How do we say it? What did we say it? It was
The TUDelft, Technical
TUDelft,
University of
TUDelft.
Delft.
I would highly recommend people check it out because the
Yeah.
stuff that's going on there is kind of extraordinary. There's amazing. I keep finding all sorts of neat things going on there. So
Yeah, there's, I mean,
I'll have to come and visit
loads
one
of
day.
things here. Yeah, you're very welcome to come
Yeah,
by.
I'm gunning for ESA Day this year,
Oh yeah,
and so if I'm in the hood, I'll have to.
if you're over, come by.
Yeah.
I'm sure Bart we had on last month will also be happy to have you.
Oh
We'll
yeah, I want
show
to.
around.
Yeah, there's a bunch of people there that
Oh, yeah.
I gotta hang out with. I gotta have some pickled herring and
Oh yeah.
you know.
I'll leave you and Bart to have the pickle herring. I'll
Yeah.
have the cheese and the beer.
Okay, very good, very good. Yeah, the beer. I'm looking forward to that too, actually. But all right. Well, look, thank you very much, everyone. I will say thank you again. Thank you to the chat, of course, for all the great questions. Thank you, as always, to Agne for making this happen. And I don't know if Cal was in there. And Cal, there you go. Chat, you've been kind and beautiful as always. Cal is what I call the hammer. She's the one who makes sure that no one gets out of control, and she's fantastic at it. So until we geek again, I will say be brave, be kind, be brilliant, and cheerio and huzzah. And I will take us offline.